In this video, we are going to construct confidence intervals for population means. We're going to start off the quick way by using the confidence level output from the summary statistics output from the Descriptive Statistics tool in the data analysis package. So if you have the data analysis tool, I will remind you how you get this output here. You go to Data, Data Analysis, Descriptive Statistics. We have our input range A1 to A41 because that's where I have all my data. I have a label in the first row, that's why this box is checked. Since I already have the summary statistics, I'm not even going to ask for those again. I'm just going to go straight for the confidence level for the mean. I will have it put the output over here. So then I can discuss it when we do the confidence interval interpretation. Okay. And here's what you get. So if I widen this here, you see you're getting the confidence, it says confidence level 1.5545. Well, what does this mean? It's obviously not a confidence interval. The confidence level is the 95%. So what is this 1.5545? Turns out that is the margin of error. So what this confidence level output is in the summary statistics is the margin of error. And when you construct a confidence interval from the mean, you are going to get your left endpoint by finding the sample mean minus the margin of error, and you get your right endpoint or your upper bound by taking the sample mean and adding the margin of error. So doing it easily like this, you go equals the sample mean was in our summary statistics. So here's our sample mean. We will subtract the margin of error. So we see up here sample mean minus margin of error, and we get the left endpoint, 2498.34. Now we do want to keep this to 2 decimal places because our original data has 1 and we can go 1 more decimal place beyond our original data. Then to get the right endpoint, we'd add the margin of error to the sample mean. So sample mean plus margin of error, and here is the right endpoint, 2501.45. So the interpretation is a simple sentence that says, we are 95% confident that the population mean PSI that the concrete can withstand is between 2498.34 PSI and 2501.45 PSI. It's important that you include the units on these because every problem will have different units. We're not working with proportions or percentages, we're working with actual measurements. So we are 95% confident that the population mean PSI that the concrete can withstand is between 2498.34 PSI and 2501.45 PSI. This tells us that 95% of the time, this method we used will give us an interval that indeed captures the population proportion. But 5% of the time, 5% of the time we could get a strange sample that is not really representative and misses the mark. Basically, its interval doesn't actually capture the population mean. So that's the quick way to get your confidence interval if you can get the margin of error from your data analysis tool. The other way would to be compute the margin of error on your own. The margin of error is the maximum likely difference between the sample statistic and the population parameter. This is the definition of margin of error, the maximum likely difference between the sample statistic and the population parameter. Well, what does that mean? We need to work with our sampling distribution, and the sampling distribution of means is, I'll say approximately normal, which means bell-shaped, right? But even more specific type of bell shape. And it's approximately normal and is described using the t-distribution. So the t-distribution is approximating the normal distribution. Here I have a graph of both the standard normal and the t-distribution. The standard normal is in blue and the t is in red. The t-distribution is different for different sizes, sample sizes. Right now this is for a sample size of 20. If I make it smaller, sample size 10, we see then there's a bit more of a difference. If we go up to 30 for the sample size, there's very little difference. But this is what we use to approximate the standard normal. Well, why do we have to approximate the standard normal rather than just using the standard normal? And that is because smaller samples have more variation than larger samples, and the t-distribution takes this into account by being different for different sample sizes. The tails are thicker than the standard normal, indicating the greater variation. So going back to the picture, see, down here you can see the red, which is our t-distribution, is greater above the blue, and it is even more noticeable with smaller samples. So I put a sample size of 10, you can see the gap right there. So this tail here is thicker out in the ends. It's thicker than the standard normal because there's more variation, so you have more data further away from the mean. So we use a student, or it's also originally called the student t-distribution. I'm just calling it the t-distribution here because in Excel they just call it t.dist. So the t-distribution is what we use to find our margin of error. And let me just show you a picture of what the margin of error is. So as I showed you, the t-distribution is, let's actually go back here. Well, let's see. Let's do this. Let me go back over here to t-dist. Move this out of the way. So here's our t distribution. It's bell-shaped. We're working with the red, and so if we want to define likely as the middle 95%, we have 2.5% distributed equally into each tail. The mean is right in the middle, okay? So this would be, theoretically, this is the population mean that we are trying to estimate. This is a distribution of sample means, right? So it's a distribution of x bars, because x bar is the sample mean. So this is a distribution of sample means, and the population mean theoretically is in the middle. Move this down a tad, right? And you see for the t distribution, there's that 0, 0 there. So this is 95% of sample means that are computed will fall in the middle here within approximately 2 standard deviations. So actually, let me make this more accurate. Let's see, what can I undo? That was the first thing I did. So let's see, let's just draw it a little bit better. So actually here, see, it would be here and here, right? So approximately 2 standard deviations away, it could be slightly more. So right through this, okay, this then is the middle 95%, right? Here is the population mean. So this is our theoretical distribution for sample means. And so there's a 95% chance that when we compute a sample mean, it's somewhere in here. Okay? Well, what's the worst possible scenario? It's barely in there, right? So maybe our sample mean is just barely in there, just hanging on the edge. We want to create an interval around it that gives us the 95% confidence we actually have included this population mean in that interval. So that means if I'm barely in here, I'm barely going to capture the mean if I make my interval this wide. So that would be the width I'd have to add and subtract, right, to the sample mean we computed to get the confidence interval. So this distance here, right, this distance here, that is the margin of error. It is the maximum likely, right, and we're defining likely with our confidence interval. It's the maximum likely difference between our sample statistic and the population parameter. And so 95% likely is defined as likely. So we know this distance then is roughly 2, right? The distance is roughly 2. Okay, distance is roughly 2, but more specifically, it's going to be determined by the particular t distribution, which depends on the sample size. So this will change for different sample sizes. This will change. So it'll always be approximately 2. It could be a little bigger than 2 with a larger sample size. It could be a little smaller than 2. The standard normal, okay, the standard normal value is at more specifically 1.96. So I'll just go over on this side to make it a little easier. This will be the negative. But if you were working with the standard normal and the z-score, remember, because the standard normal is a z distribution, the standard normal, you're 1.96 standard errors away rather than exactly 2. Over here, then, we will be always greater than 1.96 because the t-distribution has more variation. So it'll be, our t-score will always be roughly 2, but it'll be bigger than 1.96, and which is then roughly around 2, and it could even be a little bit bigger than 2. So this is where we get the margin of error. It's from this t-distribution. So now let's go back to our example here and talk more about this margin of error. So the margin of error is approximately 2, but it differs for different sample sizes based on, well, the sample size, and so the t-score will be roughly 2, but a little bit different. So we put t in here because it's different for different sample sizes, times, and then to find out that margin of error, that distance, it'll be roughly t standard errors away, because remember, the standard error is the standard deviation for a sampling distribution. So within 2 standard deviations of the mean, we say standard errors for the sampling distribution. So t tells us how many standard errors we are away. The standard error is here, so then we know how many standard errors by multiplying, and that will give us the margin of error, that maximum likely difference between our sample statistic and the population parameter. So this is how we compute it. What is the standard error? Well, that was also given to us in our output. And so if we go back to our output, here is the last piece of output information that we did not yet discuss, the standard error. So the standard error for a sampling distribution is going to be smaller than the standard error for just a single value of x, for just x for individuals. So standard error is always smaller than the standard distribution, standard deviations of the populations from which they're drawn, right? The populations are for the individuals. The sampling distributions are for sample statistics, which are averages for groups. And so when you're taking groups, you're going to have less variation in the averages than you actually have with the individuals in a population. So the standard error will always be smaller than the standard deviation of the population from which it is drawn. The standard deviation of the population is estimated here, this 4.86. So it is actually defined as the standard deviation divided by, I'm going to write it over here, standard deviation divided by the square root of the sample size, right? Because it's going to change, the variation varies according to sample size. More variation in smaller samples, less variation in larger samples. So the standard error completely depends upon the sample size. So it's the standard deviation divided by the square root of the sample size, and we can confirm that here. I can show you there's the standard deviation divided by the square root of the sample size, which is the count, recall. See, and there's the same value, 0.7685, 0.7685. So that's how we can get the standard error if we didn't already have it output here. So if we needed to compute the margin of error ourselves using t times the standard error, we saw that as long as we have the standard deviation and sample size, we can figure out what the standard error is, since the standard error is standard deviation divided by the square root of the sample size. And then we can find our t-score using Excel. So remember when I showed you, and I'll go ahead and come back here and remind you. So remember when we were looking at our curve here, we saw that when we have the middle 95% of our data, roughly the two standard errors away, here's the 95% of our data, okay? It's roughly two standard errors away, and it's different for different sample sizes, right? It's different for different sample sizes. So this here will be a t-score that's roughly 2. So we need to figure out what is that t-score based on the sample size. What is used to determine how much variation is in the t-distribution is actually the degrees of freedom, which I discuss more in other videos. And the degrees of freedom is, of course, dependent upon sample size, and it's actually 1 less than the sample size. So for a sample size of 10, this curve is drawn with degrees of freedom equal to 9. This was drawn with degrees of freedom equal to 9. If we change it to 20, it would be degrees of freedom 19. So degrees of freedom, confidence level, we need to know these things in order to find the t-score. The way the t-score formula, I will say, in Excel works is, though you don't insert the 95%, you insert what remains, which is the 5%. And that's called the significance level. So we're actually going to use a significance level, or I'll just say significance, of 5%, and it's distributed equally into these two tails. So what you need to know is when you're finding the t-score, you're going to use the significance level. So for a 95% confidence, our significance level is 5%, so they will ask for this value as a probability. And they want to know the degrees of freedom, which is 1 less than the sample size. So coming back here, we want to find the t-score, and here is what we are going to use to find that t-score. We are going to use an inverse function. T.dist is if you're finding areas and probabilities. T inverse is when you're finding t-scores. So we find t-scores using T inverse, and we have two tails. So see here, here's that 5% divided equally into two tails, and the degrees of freedom is n minus 1. So I go equal T, oops, I forgot to type my equals T dot INV, right? Here we are, two tails, 0.05, because that's the significance level, comma, our sample size here was 40, remember, so we're subtracting 1 and it's 39. You could just type in 39. I just want to remind you where the 39 would come from, and we hit enter, and here's our t-score. And notice it is roughly 2, but it's actually a little bit bigger than 2 because 40 is a relatively small sample size. So 2.02269, and now we can find our standard error using that. So if we come down here, let's find our, well, we already have our standard error, my mistake. Now we can find the margin of error. So let's actually come over here to our statistics output, our summary statistics output. All right, so here's the margin of error. I will write that here. Let me move this out of the way. So our margin of error is right here. it is equal to a t-score times the standard error. We just found our t-score, 2.022. So let's go grab that from over here. So there's our 2.02269, which is in cell F27. And then we multiply that by the standard error, which we can use over here, right? Here's the one we actually computed. And then there's that margin of error of the 1.5545, right? So there it is. And then you would add and subtract that to the sample mean. So if you have the data analysis tool, of course, it's going to be much faster. If you don't have the data analysis tool, you would need to compute your standard deviation, your sample standard deviation using stdev.s. You then would find the standard error by dividing that standard deviation by the square root of the sample size. You would need to find your t-score using t inverse dot 2t with the 5% if you're doing a 95% confidence interval and n minus 1 for your degrees of freedom where n is your sample size. And then once you have your t-score, you can compute the margin of error yourself by multiplying that t-score with the standard error you computed, right? And then once you have your margin of error, then you go finally to finding the endpoints where the left endpoint is sample mean minus margin of error, and the right endpoint is sample mean plus margin of error. The interpretation is a sentence. We are 95% confident. You always want to have your confidence level in the sentence. You want to say what it is you are estimating. So it's always going to be a parameter. So it'll be population mean because it's a parameter. 95% confident that the population mean. So you always need to have your confidence level, the parameter you're estimating, and when you put your endpoints in there, make sure that you have your units. So that is how to construct a confidence interval and how you can do it using Excel or just doing the computations if you need to yourself. Of course, I used Excel to find the t-score. You can also find t-scores using tables, but I don't talk about that in my videos. If you're interested in more about the sampling distribution of the means, I have another video that talks about the central limit theorem, and that is the theorem that tells us that the sampling distribution of the means is approximately normal, and that's why we use a t-distribution. And it explains, or that's also the theorem that tells us that the standard error is computed as the standard deviation of the population divided by the square root of the sample size that was drawn from the population. So if you're interested in more details about the theory, check out the video on the central limit theorem. And thank you for watching. I hope that this was helpful.